You can always wait till more. But if I do, yeah, because I mean, it's the only but you guys are doing that. It's the way they do it.
What it is, say, people who-
Yeah. So.
I
Okay, again, there's an additional worksheet if you haven't picked one up along with the key. We're going to continue with our test review packet, page 21. Okay, so let's start off with number one. Determine the max and min values on the graph. This is going to be application of extreme value theorem. So the only condition that's required for extreme value theorem is continuity. Our function is continuous. There's nothing that will cause, I mean, there's an x squared plus 1, but if we try to set that equal to 0, there's no real numbers that can cause the denominator to be 0. There's no vertical asymptotes here, so we can go ahead and state our function is continuous. And remember, with extreme value theorem, there is no sign line. Right? You're just finding critical points, and then you're just testing critical points and endpoints into your original function. So page 21, go ahead and try number one, see how far you can get. Again, you can use your calculators. Again, we don't use sign lines because we're not concerned about finding relative max or relative min. We want to find the absolute max and absolute min. So we do take into account critical points, but we also are relying on endpoints as well. Okay, so if I want to find the critical point, got to find the derivative. To find the derivative, what process do we have to involve here? Numerator, denominator, we have to use what? Quotient rule, yeah. Again, with quotient rule, we don't cancel anything out, right? We have to spend the time to just focus on our numerator here. Once we find our f prime, set the numerator and denominator equal to 0 to find our critical points. If we try the denominator, we're going to end up with imaginary numbers, so nothing here, because we're going to end up with x squared equals -1. Can't take the square root of negative numbers, so we can just focus on our numerator here. Take the square root of 1, I get plus or minus square root of 1. So plus or -1 are both our initial critical points, but are both of these valid? Are both these valid critical points? So we're going to test both of them. Yeah. Yes, because they're both inside the interval, right? But anytime you find critical point with extreme value theorem, we always want to make sure that we're always confirming with the endpoints, right? Sometimes all your critical points may be outside the interval. If that's the case, then you're just going to test endpoints. And by testing endpoints and critical points, we mean plugging them back into the original function. Okay, we just want to find the absolute max, absolute min. We don't care about the x values. Absolute max is 1. Absolute min is -1. All right, number 2. Rolle's theorem. Rolle's theorem feels a lot like mean value theorem. It's where our average rate of change is matched with the instantaneous rate of change, and we're trying to figure out where on the curve is the graph experiencing this average rate of change. The difference between Rolle's theorem and mean value theorem is that the average rate of change here has to be ending up giving us a slope 0. But mean value theorem can be slope 0, can be slope 1, can be slope 3. It'll be any real number. But we just have to find the order pair still and confirm that the slope is ending up giving us 0. We have a polynomial, 2 conditions associated with Rolle's theorem, continuity and differentiability. Let's make sure we state those conditions. Continuity with brackets, differentiable with parentheses. First things first, let's find our endpoints. So we can confirm that this piece ends up giving us a slope 0. So it's not because this is 0, it's because the slope is 0, right? Because the slope between the endpoints is change in y over the change in x. And 0 over 5 is a real number. It is 0. So that confirms that Rolle's theorem can be applied. We know there is going to be a slope 0 somewhere along this curve. And now we're going to make the derivative tell us where that slope 0 is going to exist. So to find f prime, we have to go through what rule here? What do you see? Yeah, 2 parentheses being multiplied together, we have to use what? What rule? Product rule. A little bit of, maybe a little bit of a chain rule, but chain rule, there's not going to be much inside that x plus 2. But you could also expand this out. I guess it wouldn't take that much time. You could just flow this out, distribute through. I'm going to go through product rule, but you could go through expansion. It won't take that much longer. Okay. F prime g plus fg prime. Okay, going to FOIL all this out here. That's really x plus 2 times x plus 2, right? I'll pull the 2 out in front here. Multiply the parentheses here, get x squared minus 1x minus 6. Let's see if I can clean this up even more. We know that there's a slope 0 somewhere along this curve, so I can put 0 in for f prime. I can just focus on factoring here. Okay, so we have our potential C values. Are both of these valid? Where do our C values have to live? In between. Okay, so in between the intervals. So which one do we have to eliminate? -2, yeah. So our C value endpoint is not close enough. It has to be inside the interval. So our C value is just 4/3. All right, try number 3. Mean value theorem, exact same process. Continuity, differentiability, find your endpoints, find your slope, find your derivative, set them equal to each other. Let's try number 3. Okay. Order pairs, endpoints first. Find your slope between your endpoints. There's our slope target. Now we can focus our attention on building our derivative. So there's my slope target. Here's my derivative. I can put that -1 into my slope variable. I can focus on solving for x. So from this stage here, I do want to point out, this is what I saw on the quiz. I saw some students do this where they started getting the x's together and the constants on the other side. So they added 2 to both sides. Get 1 is equal to 3x squared minus 2x. And I say, okay, this is relatively easy to factor. So I just factor an x out. Set x equal to 1. Set 3x minus 2 equal to 1. 3x equals 3, x equals 1. What's the issue with this process? This all feels like it's mathematically okay, but what's the issue here? Why can we not do this? Does it look okay to you? Any thoughts? Yeah, I know this feels like a process that makes sense, but this number has to be 0 if we want to start setting the factored parts into the other side. So I know this feels like, okay, there's no big issue here. This is not going to end up giving us all the right answers here. So this needs to be 0. So if I want to make that 0, I have to go through trinomial factoring. I know some students want to do this way because they feel like, well, it's a lot easier to factor 2 terms than have to deal with a trinomial factoring. But this way, there's no way to avoid it. Okay, so we have to bring that -1 over to the right side, and the constant, it has to be together with the variable. Okay. Now we can solve for x. Again, our c values have to live between the interval. So 1 is not close enough. It's on the endpoint, has to be between. So only -1/3 is going to keep. The 1 is out. Okay, I want to make sure I get in another optimization problem. So we can turn to page 26. Let's see how much we can do on our own. We've done a couple of these over the past few days. So let's see where we are building it from the beginning on our own. Page 26. Open top or closed top? Closed, yeah, because it looks like they have materials for both the top and the bottom. We have to account for 6 surfaces, right? So identify the areas of each of the 6 rectangles. And then we need to then multiply in the cost associated with each side. It's asking for dimensions. So after we solve for x, we have to find the length, the width, and the height. So if I do 1.882 times 3, that will give me the longer side length here. And then the height, we should be able to have a formula for height already set aside. We do. H equals 50 over 3x squared. That's going to get us 4.706. The problem doesn't ask for cost, but if it did, you would put it into any of these cost equations, and you'll get $637. Any questions with this optimization problem? Okay, let's turn all the way back to the beginning of the packet here. Page 2. I don't think we've done page 2 yet. Page 2 is a curve sketching problem where from the original function, you're going to build out your sine line, your concavity sine line, and then you're going to sketch your graph. So you'll see a problem like this, similar to this on your test as well. So find your derivative, go through your first derivative test, create your slope sine line, find your second derivative, create your second derivative sine line, and then once you have your sine lines all laid out, then you can find your relative max, your relative min, your concave down. And you can also sketch your graph based off of the shape, the slope, and the curvature of the graph. So from f prime, we have mixed fractions here. We can get common denominator, so we can clearly see where the critical points are. A common denominator is x to the 1/3. I balance the second fraction. I get 8 minus 4x to the 1/3 over x to the 1/3. Set the numerator equal to 0. Set the denominator equal to 0. I'll get 0 and 8. So test -1, test 1, test 9. I see my graph is decreasing to relative min at 0, increasing to relative max at 8, decreasing after that. We can write out all of our because statements for increasing, relative max, and relative min. All these relative max, relative min, y values, they come from the original function. Moving to second derivative, we can go through power rule again. Clean up our second derivative, set the numerator and denominator equal to 0, but only denominator will produce any critical points for us. So 0 is the only critical point. If I test both sides of 0, there's no change in signs, so there's no point of inflection. So from these order pairs, and from our graph here, we know there's a sharp turn at 0 since, our slope is undefined at 0. We know there's a relative max at 8. We know the graph is going to be concave down for the entirety of the graph. And then the statement about concave down is all real numbers except at 0 because f double prime is less than 0. All right, your homework is just page 22. I'll send out a reminder this afternoon. Tomorrow morning, I'll have a full help session starting at 7:30. Friday, again, I'm not going to be able to do a full help session. I have a meeting at 7:45, so I can be available though Friday, do a half session from 7:10 to 7:45. And yeah, I'll be working off of those the new review packet for tomorrow's session. All right, computer folks. Okay. All right. Yes. Well, it's just up there. Oh, we're talking about this one here? Yeah. Actually, first row. Yeah. Copy this here. This is this one just picked up. Oh, this is what your test was. Where's that a little bit? This is no problem. I mean, I've seen people do it. Sure. Or like sometimes. They're like, I think it's only 5.